Good morning, students. This is Gopi Krishna, lecturer in mathematics, KA and HL Degree College, Yelluru. This is the class for the final BSc, 5th sem, paper 5, that is the ring theory and vector calculus. This is class number 8 of Unit 1 rings. Now, in the previous class, we have learned the definition of subring and the necessary and sufficient condition theorem on subrings. What is that? If S is non-empty set in R, ring R, then S is subring of R if and only if A minus B belongs to S, comma A dot B belongs to S, for all A comma B belongs to S. By using this theorem, we have proven two theorems, and also those are intersection of two subrings is a subring, and the second one is intersection of arbitrary family of subrings is a subring. Next, after that, we have proven another theorem, that is union of two subrings is again a subring if and only if one is contained in another. These are the theorems we have discussed in the previous class, and also the definition of the subring. We have learned the definition of the subring in the previous class. Now we are learning the definition of left ideal of a ring. A non-empty subset U of a ring R plus dot is called left ideal of R if the first bit A comma B belongs to U implies A minus B belongs to U. This is called subring condition. I think it is not subring, it is, again I am repeating the left ideal of a ring definition. A non-empty subset U of a ring R plus dot is called left ideal of R if first bit A comma B belongs to U implies A minus B belongs to U. This is a subgroup condition, that is S is subgroup of R. The second one is A belongs to U, comma R belongs to R, then RA belongs to U. R is on left side of A, where A is an element in U. R is element in big set R. So R is on left side of A. R dot A belongs to U. Then that U is said to be left ideal. If these two conditions are satisfying by a non-empty subset U, then U is said to be left ideal of that ring R. What is right ideal definition? Same, the writing theory is same. A non-empty subset U of a ring R plus dot is called right ideal of R if the first bit is same, A minus A comma B belongs to U implies A minus B belongs to U, and the second one is A belongs to U, comma R belongs to R implies A dot R belongs to U. If you observe that A is in U, R is in the big set, that is multiplying on right side of A, is it right? A R belongs to U, R is on right side. Then we say that U is right ideal of R. If we observe the difference between the left ideal and right ideal, that is only the difference is A is multiplying on right side, sorry, R is multiplying on the left side of A, then it is said to be left ideal. If R is multiplying on the right side of A for A, then U is said to be right ideal of the ring R. What is the definition of ideal? The writing is the same for this one also. A non-empty subset U of a ring R plus dot is called ideal of R if the first bit is same. A comma B belongs to U implies A minus B belongs to U. Left ideal first bit, right ideal first bit, and the ideal first bit are equal, are all same. What about this second bit? A belongs to U, comma R belongs to R. A is in U and R is in big set R. Then R dot A belongs to U and A dot R is also belongs. R dot A belongs to U and A dot R belongs to U. If R is multiplying on left side, then we say that left ideal. If R is multiplying on right side, then we say that right ideal. Here both are there. That means both and left and right ideals. If U is both left and right ideal, then U is said to be an ideal. Okay. Ideal definition is, again I am repeating the definition of ideal, a non-empty subset U of a ring R plus dot is called ideal of R if the first bit A comma B belongs to U implies A minus B belongs to U. The second one is A belongs to U, R belongs to R implies R dot A belongs to U and A dot R belongs to U. If U satisfying these two conditions, then that U is said to be an ideal of the ring R. Okay, by using this definition, we prove the theorem number 12. What is that? Intersection of two ideals of a ring R is ideal of R. For that, I am taking two ideals. Suppose S and T are two ideals of ring R. We prove that S intersection T is ideal of R. Because S is ideal, T is ideal. That means, first of all, what is the ideal definition? I am repeating again that in that ideal definition, there are two bits are there. The first one is subgroup condition. Is it right? Subgroup. Subgroup means closure itself is a group, the smallest group in the group R. R is ring. This is also a group. S is subgroup. That means S is group. Group means it satisfies four laws. What are they? Closure, associative, identity, inverse. So there is an identity in S and T also, because these two are sub ideals. Ideals means subgroups. Subgroups means groups. Groups means identity law exists. That means identity elements are there. That is 0 belongs to S. 0 is the identity element in S. And also 0 is the identity element in T. That means 0 is both S and T means 0 belongs to S intersection T. S intersection T has an element 0. That means S intersection T is non-empty set. Clearly we say that S intersection T is contained in R because S and T are ideals of R. S and T both are in R. That means S intersection T is also in R. Okay, right. Now I am taking that A comma B belongs to S intersection T, and I am taking that R, small r, is in the big set R, that is ring. Now A comma B are in S intersection T means A comma B both are in S and also in T. A comma B belongs to S and A comma B belongs to T. And R belongs to R is writing in the both cases. A comma B belongs to S and A comma B belongs to T. What is S? S is ideal. By the definition of ideal, we are writing two bits, that is A minus B belongs to S and A dot R belongs to S, R dot A belongs to S. If we observe that in the ideal, the two bits are A comma B belongs to U plus A minus B belongs to U, R dot A dot R belongs to U. Similarly, here S is a ideal means A minus B belongs to S, A dot R dot A both are in S. Similarly, for A comma B belongs to T and R belongs to R, T is an ideal. Again, we are applying the ideal definition, that is A minus B belongs to T, A dot R belongs to T, comma R dot A belongs to T. Okay, right. Here we observe that A minus B is in S and also A minus B in T. Students, kindly follow the cursor. A minus B belongs to S and A minus B belongs to T. That means A minus B belongs to S intersection T. Similarly, we observe that A dot R belongs to S and A dot R belongs to T. A dot R belongs to S and A dot R belongs to T means A dot R belongs to S intersection T. Similarly, if we observe that R dot A belongs to S and R dot A belongs to T, that means R dot A belongs to S intersection T. That means A minus B, A dot R dot A, all are in S intersection T. Therefore, S intersection T is ideal of R. We have taken S and T are two ideals in R, and their intersection, S intersection T, is ideal of R. Hence, intersection of two ideals of a ring R is ideal of R. Okay? Now, we go to the next theorem. That is theorem number 13. What is that? Intersection of arbitrary family of ideals of a ring R is ideal of R. Okay? Proof. Suppose set of R Si such that each Si is ideal of R. This is the arbitrary family of ideals of ring R. We have to prove that this arbitrary family intersection, that the intersection of this arbitrary family, that is intersection of Si, is ideal of R. We know that each Si is ideal. That means each Si is subgroup. Subgroup means identity exists. 0 belongs to Si for all I. That means 0 belongs to intersection of Si. 0 belongs to intersection. Therefore, intersection of Si is a non-empty set because 0 is in intersection of Si. That's why intersection of Si is non-empty set. Each Si is in R. Is ideal of R means each Si is in R. That means intersection of Si is also in R. That means intersection of Si is contained in R. Now I am taking that A comma B belongs to intersection of Si and R belongs to R. A comma B belongs to intersection of Si means A comma B is in each Si. That means A comma B belongs to Si for all I and R belongs to R is written same from the first step to the next step. A comma B belongs to Si and each Si is ideal. We know that each Si is, students kindly follow the cursor, each Si is ideal. Each Si is ideal means by the definition of the ideal, A minus B belongs to Si, A dot R belongs to Si, R dot A belongs to Si for all I. That means A minus B is in Si for all I. That means A minus B is in each Si. That means A minus B belongs to intersection of Si. And also A dot R belongs to each Si means A dot R belongs to intersection of Si. And also R dot A belongs to each Si means R dot A belongs to intersection of Si. That means A minus B, A dot R, R dot A are all in intersection of Si. That means intersection of Si is ideal of R. What is Si? This is a family of ideas. First line of the proof. Si is a family of ideals. That a family of ideals intersection, that is intersection of family of ideals Si is an ideal of R. Hence, intersection of arbitrary family of ideals of R, ring R, is ideal of R. Next, we go to the theorem number 11. Sorry. That is, union of two ideals of ring R is ideal of R if and only if one is contained in another. Or directly, it can be questioned as if S and T are two ideals of ring R, then S union T is ideal of R if and only if either S is contained in T or T is contained in S. We have proven this theorem previously for the subrings. The necessary condition is same proof as in the subrings proof. That means necessary condition is same, but by replacing, you can write the same proof by replacing with subring with ideal. Instead of subring, you can write ideal. Then you got the same proof. The necessary condition proof is same. So you can follow the previous class and the previous material which was posted in your WhatsApp group. You can go with that and you can recollect it and try to write this necessary condition with your own. Is it right? I will go to explain the sufficient condition. What is the sufficient condition? If we take S union T is ideal of R, then we have to prove either S is contained in T or T is contained in S. In contrary way, we assume that S is not contained in T and T is not contained in S. The theorem proof for this sufficient condition is also the same as in subrings. But what is the difference? Main is in that theorem we've written subring. In this theorem we write ideal only. The same proofs are applicable, and this step is only the difference between the These two steps are only the difference in between these two theorems. Okay, here we write only the definition of the, by using the definition of the ideal only. The remaining part is the same as in the subrings. So students, all of you want to do the proof, and you have to write the proof with your own by taking the reference of the subrings proof. Okay, so students, I am giving the work to you that you have to prove this 11th theorem with your own by taking the reference in the subrings topic, okay, in the previous class. Okay, right. Thank you.